Hello, everyone. I hope you are all healthy and well. Welcome to the next talk in our Golden Webinars in Astrophysics series. Our speaker today is Karen Meech, who is an astrobiologist at the University of Hawaii. My name is Paula Ronco, and together with Thomas Pusia, we have organized today's webinars for you. As in our previous webinars, simultaneous language interpretation is provided by Patricio González, who will be simultaneously translating for us into Spanish. En sus dispositivos pueden escuchar la interpretación al español de la conferencia al pinchar el botón de interpretación que se encuentra en la parte inferior derecha de la ventana de la aplicación Zoom y seleccionar español. We would like to acknowledge the generous support of the Center for Astrophysics and Related Technologies, also known as CATA for its Spanish acronym.
Thank you so much for your feedback and comments. We really appreciate it. And we always take advantage of it, so please keep them coming. If you're watching a recording of this talk on YouTube, please leave your comments below in the section below the video window. If you would like to support the series, please send us feedback. You can find the email in the announcement emails that we send around. If you have any questions during the talk, please type them in the Q&A window. You can also upvote questions and comment on them. And you can have interactions with the person who is asking the question. And we will select then the best questions for the discussion after the talk. The link to the live version of this video will be automatically taken down by YouTube shortly after the streaming ends, but we will upload the higher resolution version in both English and Spanish to our YouTube channel a few weeks after the talk. So before we begin, we would like to introduce, of course, all our panel members that are with us today. Karen, the speaker, Patricio, Paula, and myself. From the Institute of Astrophysics at Pontificia Universidad Católica, we have today my new colleague, Cristobal Petrovic, with us today. And also from the Institute of Astrophysics, we have Elizabeth Artur de la Villamor, our postdoctoral fellow from the Institute with us.
We have also the great pleasure to welcome our guest panelists today. We have Daniela Lázaro, who is a professor and researcher in astronomy at the Observatorio Nacional de Rio de Janeiro, Brazil. Millarca Valenzuela, who is a geologist and professor at the Departamento de Ciencias Geológicas en la Universidad Católica del Norte, Antofagasta, Chile. Meredith McGregor, who is a professor of astronomy at the Department of Astrophysical and Planetary Science in the University of Colorado Boulder. Julio Ángel Fernández, who is a professor of astronomy at the Facultad de Ciencias, Universidad de la República, Montevideo, Uruguay. We also have Jorge Cuadra, a researcher at the Millennium Nucleus of Planet Formation and also professor of astronomy at the Universidad Adolfo Ibáñez. Dan Weddermer, chief scientist and co-founder of the SETI Home Project at the Berkeley SETI Research Center. Jean Raymond, an astronomer at the Laboratoire du Astrophysique de Bordeaux in France. And of course, always Paul Honingen-Huey, who is a professor of philosophy, Institute of Philosophy at the Leibniz University Hanover in Germany, and also lecturer at the Department of Economics at the Universidad of Zurich. And last but not least, we have our excellent Q&A manager, Simon Angel. So it is our great pleasure to introduce Karen Meech as our Golden Webinar speaker today. Karen received her bachelor degree from the Rice University in Houston in 1981. She then got her PhD in planetary science in 1997 and at the Massachusetts Institute of Technology, where she also served as a teaching assistant. After finishing her PhD, she moved to Hawaii, where she first became an assistant astronomer, then associate astronomer in 1992, and finally a full astronomer at the Institute for Astronomy in the University of Hawaii in 2000. During her career, Karen received many awards, such as the Annie Jump Cannon Award in 1988, also the Harold C. Urey Prize in 1994, which recognizes and encourages outstanding achievements in planetary science by an early career scientist. Several NASA Group Achievements Awards for the Stardust Flight Team and the EPOXI project, and the ARC's distinction for being the Scientist of the Year in 2018. She has even a main belt asteroid named in her honor.
Karen is an expert on planetary science. She specializes in characterizing the Earth's primordial water through studies of deep mantle rocks and combines this information with our knowledge of the asteroid belt composition to understand where did the water on Earth come from. She also works on the formation of habitable worlds and studies comets, which are icy leftovers of planet formation processes that can provide clues about the chemistry and dynamics in our solar system. Karen was a co-investigator of the Deep Impact mission of NASA, designed to study the interior composition of the comet Tempel-1 by releasing an impactor into the comet on the 4th of July in 2005, the EPOXI and Stardust-NeXT missions. Her role as a science team member was to coordinate all of the ground-based observing support for these missions. She has published lots of research papers and led the characterization of the first interstellar object, Oumuamua, maybe you remember, discovered by Pan-STARRS in 2017. She's also extremely active in the educational area as the chair since 2018 of the IFA Institute for Astronomy graduate program. So now we would like to hand it over to Karen, who will tell us today about the archaeology of habitable worlds using small bodies to unlock the past. Karen, we are all ears.
Thank you very much for the lovely introductions. All right, well, what I like about this topic is that it's very interdisciplinary. And when you're starting out in a career, especially as a graduate student, you're getting more and more expert in a narrow area. But what's exciting about this field is how the funnel is opening up again, and you get to play around in a new toy box and connect together different disciplines. So let me start by giving you a broad overview of why this is so fundamentally interesting, the topic today. You know, basically, one of the most profound big picture questions that has been asked since ancient time has been, are we alone? Ever since people started to look up at the sky and wonder what's out there. Of course, today we have a very different perspective from the space age, but it's equally profound as we start to look at our world from the position of space. As Voyager 1 was heading out of the solar system in February 1990 at a distance of about 6.4 billion kilometers, our planet looked like just a pale blue dot in space. And as Carl Sagan noted in his book with the same title, our planet is a lonely speck in the dark. The Earth is the only world known so far to harbor life, and that's likely because of water. Now today, this question is framed in terms of the interdisciplinary field of astrobiology, and this is a field that I've really gotten engaged with, and I'm embracing the field because there's so many more answers you can get by bringing together different disciplines. And one of the fundamental exciting questions about astrobiology is to try to trace the process of how you form a world that could support life, namely, what is the physics and the chemistry of forming a rocky world like Earth. Now, where we're at today, even with the sensitivity of some of the world's largest telescopes, this is the ALMA submillimeter array at high altitude in Chile, we're starting to get a glimpse of the process of the birth of a young solar system. These are just two images that show the birth of two star systems. You can see the star in the middle, some dark lanes, which hint that maybe some giant planets are growing there and tracing out, removing some of the dust in the disk. But this is not quite yet what we need to understand how habitable worlds form, because we're not getting close enough to the star. However, it's very likely that the next generation of telescopes, the ones that are being planned for the next decade in the 2030s, will have the sensitivity and the resolution so we can start to glimpse at the scales inside the orbit of Jupiter where terrestrial planets in our solar system are. Not only will we be able to see the process of building a planet, we'll be able to get detailed measurements, chemical measurements to look at what's going on, and perhaps even image the planets. Now, as of today, March 26th, there's perhaps as many as 10,000 exoplanets known. Over 4,000 of these have been confirmed, and over 3,000 of these exist in multi-planet systems. And there's probably more than about 50 which are potentially habitable, meaning they're at just the right distance where life could survive. But the big question is, all of these extrasolar planetary systems look very different from our solar system, where we have rocky terrestrial planets close to the star and a suite of giant planets orbiting much farther out. Is our solar system unique? Does this specific architecture play a role in giving us a world that's habitable at just the right distance in the habitable zone? So specifically, the habitable zone is defined by astronomers as being the distance from the star where the planetary surface of a planet with an atmosphere could support liquid water. And so for our solar system, Earth is squarely within the habitable zone at this distance from the sun. If the star is cooler or hotter, the habitable zone will be closer to the star if it's cooler, farther from the star if it's hotter. And the habitable zone changes with time as the star heats up over time. So why is all the habitability pegged to water? Well, we think water is essential for life. Our cells and our bodies are made mostly of water. And the energy of life is the chemistry that requires water. Water is also a very special substance because it stays liquid over a wide range of temperatures, and it's less dense when it freezes, meaning even if you're at the very edge of the habitable zone or even outside, it may preserve an ocean underneath. All of this being said, if we really want to study how habitable worlds form, we actually know of only one example where there's a solar system with planets in the habitable zone that are inhabited, and that's ours. And so in fact, if we want to understand the formation, we really ought to start with our solar system. But of course, how do we do that? Because we can't watch the process of our solar system's birth. So what we really need to do is look at the leftover remnants of that process. So this is where the archaeology comes in. We want to look at the fragments and the leftover pieces that have not been altered since the time in which our planets were forming. And this typically means small asteroids that have ices and comets. So this is what I mean by small bodies, the leftovers. But before we get into that, we should note also what constitutes a habitable world. What is important for life to exist? Well, obviously, water is important. You have to have liquid water because that is the medium through which the chemistry of life occurs, brings in waste, brings in nutrients, carries out waste. We also need some organic compounds because that's the source of the energy, or what we would call redox potential. Life processes involve an exchange of electrons. Well, unfortunately, our solar system is actually quite dry in the inner solar system. Mercury is very dry. Venus and Earth, nearly twins in size. Venus once had water, but it's lost it. Although we think of our world as a blue marble or an oasis in space, it actually has very little water. And as we'll see, we don't actually know how much water we have, but it's not much. The moon is quite dry, although there's some water, and Mars on the surface is dry. So clearly, if you don't have enough water, it's bad news for life. Now, a lot of people envision when you see some of these exoplanets that if there's a world that's deemed to be very water-rich, a water world, that's a good thing, but not so fast. Because part of the process that keeps our world habitable is the cycling of a lot of the gases in our atmosphere. It keeps the temperature stable. If we have too much water, say as much as 5 oceans worth on the surface of our planet, that would cover up the continents. And that would remove one of the key weathering cycles that brings some of the nutrients that life needs, namely phosphorus, into the environment. If you have much more water than this, say the order of 50 oceans worth, the oceans would be so deep and the pressure at the bottom would be so intense, you would actually start forming ice, and you would no longer have an interaction between the rocks at the ocean floor and the water. And so we would stop bringing up some of the nutrients, creating the rich chemistry that we see at the ocean floor. So we have to have just the right amount of water. So to put the comets and the small bodies into the context of how we're going to use them as tracers, let me briefly review some aspects of building a solar system. All solar systems start as a cloud of gas and dust in the interstellar medium. Something causes this to collapse. It begins to collapse faster at the center, So you collapse down to a flattened disk that's flared at the edges with a young sun in the middle that's warming up as thermonuclear reactions start. An important concept during this time is the idea of a snow line. It's obviously warmer in the middle, colder as you move outside. At some distance from the star, it is too warm inside of that distance for things like water to be in the ice phase. Instead, they're gaseous. And outside of this distance, water would exist as a solid. And since there is so much more volatile or gaseous material in the disk, once you get cold enough, you have a huge amount of material out of which to build planets. Eventually, these tiny little grains of dust and ice start to accumulate, building first centimeter scale, kilometer scale. We get up to planetesimals, irregularly shaped, several kilometer sized bodies. Eventually, we will get giant planets. And finally, in the last stages of the formation of a young solar system, the gas and dust disappear and the giant planets, anything that's near the giant planets will get scattered outwards. And it's in this scattering outwards that a lot of the primitive materials that we would like to study get put in place and preserved for the age of the solar system. And much of this gets scattered out to this vast reservoir called the Oort cloud, which is about 50 to 100,000 times the Earth-Sun distance. We also think that comets could have formed anywhere beyond the ice line, either in the vicinity of the giant planets, which formed outside the ice line. The giant planets can scatter them out to these great distances, or they may have formed closer in the region of the Kuiper Belt, but still beyond the ice line. So these represent the primitive material that will now give us the evidence. So we want to look at these small bodies and go backwards in time and learn what we can figure out about how the solar system was put together. It's actually quite a daunting task. So these are the categories of things that you might consider small bodies that preserve the ancient history of the solar system. We have meteorites. Now, meteorites that we have in our collections today are actually fragments of asteroids. The most primitive of these are ones that have not been heated inside the asteroids. We've got thousands of samples, but what most people don't realize is we have samples from the primitive asteroids, from only about 15 so-called parent bodies. They've been well studied in the lab, and they all show that they contained a lot of water. We have icy asteroids, which are those which are in the asteroid belt region here. These have largely been unexplored, and I'll talk about these today. We've studied comets a lot, both from the ground and from missions, and I'll be talking about those. Comets, again, formed in the vicinity of the giant planets outwards. Some satellites around the giant planets are small and are very icy and are exciting from the astrobiology potential. For example, the Cassini mission showed that Enceladus, small icy moon orbiting Saturn, actually is spewing geysers of material from a subsurface ocean. Very interesting from the astrobiology point of view, but because it's big enough and has had some forces that have caused internal melting, this one isn't as good for understanding the very first stages of the solar system. And then I'll touch upon interstellar objects. They're primitive small body tracers, possibly of formation processes in another solar system. So let's start with comets. You know, people have been observing comets for thousands of years. Some of the most beautiful ancient records show records of appearance of ancient comets. And this is just a handful of some of the really bright, great comets we've had recently. But let me start with explaining how comets work and what we're going to try and use scientifically from the comets. Basically, as Fred Whipple postulated in 1950, comets are basically big dirty snowballs, roughly kilometer scale. As they approach the sun, the sunlight warms the surface, and any ices that might be present will convert directly to a gas or sublimate. And these are just three images. This one's actually Halley's Comet. This is Field 2. That's a false color composite image, so you can see the faint dust and gas as well as the nucleus. And this is Comet Borrelly. Now, when this turns on, when the tail starts to form, the dust will be ejected towards the sun, and the sun's radiation pressure will gently push it back into a tail. And the tails on comets can be millions of kilometers in length. They have both a dust tail and a gas tail, and the sunlight can then photodissociate whatever the molecules coming off of the nucleus, and so you'll get molecular fragments, or what comet scientists call daughter species. The original molecules are the parents. Now, because these preserve both the dust and the ices from the early solar system, many countries, NASA included, have been keen to spend a lot of money on space missions. And so just as an overview on some of the earliest space missions, the first one to actually visit a comet was the ICE mission. This is a International Cometary Explorer. This was originally designed to be a mission that was exploring the solar wind, flow of charged particles from the sun, but it was actually one of the three spacecraft was redirected to fly through the tail of Comet Giacobini-Zinner. Unfortunately, this mission had no camera. The next mission, though, was the European Giotto mission that visited Comet Halley. And one of the fundamental discoveries of this mission was that comets actually do have a solid body. Moreover, comets had an organic rich dust, and they were also mostly made of water, about 80% in terms of the gases coming off, some CO, some CO2, and other minor species. The Deep Space One mission was actually a technology demonstration mission, more or less to just show off how these new ion-type engines would work. But then they decided, why not do some science? And then there was a flyby of Comet Borrelly. And this was the first one to really start to show structures and perhaps some geological formation on the surface. The Stardust mission then was a really exciting mission in that a capsule flew through the tail of Comet Wild 2, shown here, and brought back some of the dust to Earth. And what was very surprising from this mission was that the dust showed that it had seen very high temperatures. That means that the dust was in the inner solar system, quite close to the sun. And at first, this didn't make sense, since comets were thought to have formed outside this ice line at very cold temperatures. So this gave us a hint that there's a lot of movement going on in the planetary disk as things are forming. And then there was the EPOXI, or the Deep Impact mission, and its follow-on missions. This mission was the first one I was involved with as a co-investigator, and this was intended to do an active experiment, impact a comet, dig a hole in the surface, and look at the fresh material underneath. And what this showed was that the fresh material is really close to the surface. So what have we learned from 30 to 40 years of ground-based comet science and these early missions? And I know any comet experts in the audience will be horrified that I'm boiling it all down to a single slide. There's a lot to cover. So let's take a look first at this diagram here. What this is plotting is about 30 years worth of spectroscopy to look at the chemistry of comets. This was done by Micah Hearn and his team. And what is plotted is chemical composition along the y-axis, looking at two particular daughter species, carbon, just C2, and an organic, CN, cyanide. And it's plotted versus where we think the comets formed. And so basically any of the ones that are in blue are what we call short period comets. We think they formed out in the region of the Kuiper Belt, so beyond where Pluto orbits today. So they formed very cold. And the purple and red ones are ones that likely formed near the giant planets, a little closer in, much warmer, but then got kicked out and today originate in the Oort cloud. So when the statistics first started to come in, it looked like most comets had pretty much the same chemistry. But then it was noted that especially some of these short period comets seem to be depleted in some of these organic compounds, the CN compounds. And so it was thought, oh, we're seeing a signature in the chemistry that must be related to temperature. However, as more and more data came in, the other types of comets are also starting to be seen to be depleted. This was not expected because you would expect differences because of the temperature of formation. come forward in time, now with the advent of spectrometers on large telescopes in the infrared technology is always lagged behind the optical. People can do the same sort of experiment, but they don't have to look at the fragments anymore. You can actually look at the parents. And what's shown here, this is just the x-axis is meaningless. It's just different comets. You can see a range of abundances for various compounds. This is methanol, and you can see some are enriched, some are depleted. Same with some of these organic species, other compounds. But what you see is that there's a complete mix-up between short period and long period. So basically, all of the chemistry says it doesn't really matter where it formed, which was puzzling. Isotopes that I'll talk quite a bit about usually can give some additional information, but this too was a confusing message. Some of the isotopes were like nitrogen was enriched in comets compared to the Earth. Carbon looked like Earth. On the other hand, if we look just at carbon monoxide, which is an ice that sublimates at very low temperatures, it was predominantly only the really long period comets that had a lot of CO, but that may be an effect of evolution because CO can disappear relatively quickly. So there's the ground-based. What about space missions? Well, to many people's surprise, one thing that the EPOXI mission showed us was that carbon dioxide was really important, and we had thought it was mostly water and mostly carbon monoxide. But with these jets that were seen on the dark sides of this comet, 103P Hartley 2, it was clear that most of the activity was being caused by sublimation of CO2. Just as we'd had hints from the ground, comets are low density, they're really good thermal insulators. And we knew that from deep impact because the fresh material is just beneath the surface, which means if you bring a sample back to Earth, you're really looking at primordial material. And as we saw from the Stardust mission, there was a lot of movement in the nebula. Now, I'm not going to spend much time on meteorites because that would make the talk way too long. But for the purposes of this talk, what we've seen in the primitive material, there was a lot of what we call aqueous alteration, meaning in the larger parent bodies of these meteorites, they heated up enough that any ices there melted. And so there was liquid water circulating in these bodies interacting with the rock. So we know there was a lot of water in the vicinity of the asteroid belt. But what we haven't seen in the meteorite collection is a piece of rock that we go, aha, this matches the chemistry of Earth. What about Rosetta? Now, this was a European mission that was launched in 2004 to go to the comet 67P, Churyumov-Gerasimenko. It arrived in 2014 and it stayed with the comet for 17 months, orbiting somewhere between 10 and 30 kilometers. So we got a detailed look at the structures on the surface, the processes. Most of these are black and white. This one more or less shows the true color of a comet, reddish, organic rich. This false color region here is showing the larger abundance of ices. We also see on this one end of the comet, it's more icy at the bottom. So what did we learn? There's a wealth of material learned from Rosetta. Some details such as there was a lot of ice and even some things that we had not seen before, which would be hard to observe from Earth. We finally got a glimpse at noble gases. A rich array of organic compounds, many of which are necessary for life. So if comets indeed did bring some of the water and material to Earth, they were full of all the ingredients you need for life. Just as we'd seen from the other missions and from the ground, this comet's low density, low strength, and it can preserve the history of the solar system. Now, all of this is fantastic, but we were left with several key questions. We still don't know completely what was original and what is the effect of processing, because we're still trying to understand how comets work. We did not answer the question of exactly how and where comets form. And this did not answer the question of, did comets bring water to the early Earth? And the reason it didn't answer it needs some explanation in a little more detail. about the early solar system. So these are two cartoons drawn by Ilse Cleves, and it's intended to show our young protoplanetary disk as our solar system was in the stage of just collapsing. The young sun is forming in the middle. This one is intended to represent the gas, and this is intended to schematically show what's going on with the dust. So if you remember, at the beginning, I mentioned that the nebula will collapse faster near the core where the density is higher. The young sun is heating the inner regions. Much of the material may get vaporized. This also heats the surface of this gas disk. And so you have a hot layer. There's all sorts of ultraviolet radiation. You have magnetic fields, you have charged particles. Underneath this layer, you'll have a warmer layer where a lot of molecules will form, a lot of rich chemistry can be occurring in here. And then at the midplane, especially in the outer disk, but even as you move into the interior, it's very cold. So a lot of these gases will now freeze on any of the dust that's in there. Now, at the same time, there's going to be a lot of movement in the disk. There can be turbulence, there can be cycling from the midplane up to the outer regions. You can have movement also radially away from the star. And during this period, the dust grains are starting to coalesce and grow. The ices are freezing on them, and you're starting to make planetesimals. Some of the tiny grains can migrate inwards, and as the giant planets grow, they're going to toss things around. So we can't decouple the chemistry from physically what's going on in terms of the formation of the planets. So let's get back to where we think water may have come from. One of the early ideas was that comets could have delivered the water. They're water rich. And one of the clues that comets could have delivered water was that people had known for a long time that the isotopic ratio in water from deuterium, the D to H in Earth's oceans, was high. And it was high compared to the interstellar medium. And we can measure the D to H in space, and we know that the D to H is very high in the interstellar medium because of low temperature chemical reactions. But the Earth had an elevated D to H even compared to the gases in our disk. What was exciting was that the Giotto mission, when it flew through the tail of Halley's Comet, actually measured the D to H and showed that the D to H in Comet Halley was elevated. It was about a factor of 2 higher than Earth's oceans. And this got everyone excited. Maybe comets brought water to the early Earth. But there's a problem. So what this diagram is showing is just the D to H ratio in various reservoirs. The x-axis is just separating the different reservoirs. So here's the interstellar gas that has been measured. And Jupiter and Saturn have a similar D to H as you would expect. They're mostly made of the gas from our solar nebula. The very first comet, Halley's Comet, was elevated over Earth's ocean water, which we can measure easily. The problem was, as more and more comets were measured, they were all very high compared to Earth ocean water. So they couldn't be the only thing bringing water because it didn't match the oceans. Some people argued, well, asteroids, the meteorites, kind of match Earth oceans pretty well. Why haven't we just solved the problem? They match. Well, that's not the only thing they bring, and some of the other isotopes did not match. Well, all of these comets were long period comets, which formed again near the giant planets. Finally, a measurement was going to be made on the EPOXI mission target 103P Hartley 2, and everyone was excited. It was a different type of comet, one of these that formed out near the Kuiper belt, and everybody expected that it would be very high in D to H because it formed colder, and the theory says D to H should be elevated at low temperatures. Well, when that one was measured, it matched ocean water exactly. So all the scientists who did the disk chemistry models were scratching their heads, and they scrambled to figure out why could the D to H ratio go down for these. And so eventually, people had some new models, and they were excited to see 67P because 67P was the same type of comet. They expected it would now be at the same level as the EPOXI target. But now 67P had the highest D to H of any of the comets. And so people threw up their hands and said, we don't know what's going on. And the team said, well, comets clearly did not bring oceans to Earth. Well, all we really know is that these comets did not bring oceans to Earth, but we already know that because those comets still exist. Well, here's some of the explanation for that. Again, our cartoon of our nebula where we get the fingerprints of the ices as they freeze onto the dust. This simple schematic shows warm in the interior, cold as you go out, but that's not reality. Here is a tracing of one disk chemical model run by Karen Willesee and Woods for one chemical species. And so here what we're looking at, the sun is in the middle. This is going towards the outer solar system. Here is the midplane. This is above the midplane. And the color code represents the relative amount of this species relative to water. Red is high. In the inner solar system, the species is abundant. And as we move outwards, it decreases, but then it increases again. And as you go above the midplane, it's complex because of the complex nature of the chemistry. So in fact, if we take a look at what's going on, this was the original expectation for D to H. It rises slowly as you go to the outer solar system and gets colder. This was the revision after we saw what happened with the EPOXI mission. So it's going down. This is a tracing of one of these models along the midplane, complex. Here's the Rosetta measurement. How would you interpret that? Well, it crosses this model in a couple places, it crosses this model. But you really want to know where that comet formed. These different colors represent different dynamical models of how you build the planets. This model says anything that got to Earth must have come from this region of the solar system. A different model predicts material that got to Earth came from a different region, and so forth. So the bottom line is a single isotope cannot tell us the story of where water comes from. So let's digress a minute, because I want to get into a little bit of why I got so intrigued by the question of where Earth's water comes from, especially after hearing people predict from the Halley mission that it was delivered by comets. First of all, you need to ask, are we really measuring the right source, the right water to compare to comets? Ocean is not the only water we have on Earth. And a few years ago, Mike Model put together a really nice review of an inventory of water in and on the Earth. Now, everybody can estimate how much is in the atmosphere, the oceans, the rivers, and you get pretty much the same result. As you go deeper into the Earth, across the lithosphere and mantle, you no longer make actual measurements. You're doing laboratory experiments under high pressures and temperatures to try to understand how much the minerals can hold and make estimates also based on seismic values within the Earth. So you can see many of the papers are on the low end. If you add up all the water inside the Earth, estimate about 1.5 ocean volumes on Earth. The high end, 11 oceans of water, but the capacity of the minerals is huge. So the Mike Model inferred that it was probably about 3 oceans, but in fact, most of these scenarios suggest that there's more water inside the Earth than outside. So in fact, we're probably not comparing it to the right thing if you're comparing comets to Earth oceans. And it just so happened in 2004, I ended up attending an astrobiology conference. And like many conferences, after the conference, there was a field trip. And I went on the field trip to look at some hot springs. And the geologist with us said, oh, this is cool water. You can go right up, you can touch it. It's primordial water. Of course, my light bulb went off and I thought, finally, that makes sense. Primordial water, we're looking at deep water from inside. I was so happy. I went to the University of Iceland geologists and they said, well, she's dead wrong. That in fact is not primordial water. That is rainwater that soaks down a little ways, gets heated up, comes out steam. So I was all despondent and said, oh, wait, we have measured primordial water. And in fact, at places like Iceland, there is a material that's coming up from near the core mantle boundary in these plumes. And that's what's creating these hot spots. And some of the material survives transport to the surface. And I asked, how do you know that this material really hasn't mixed with the interior? And the reason for that is from the measurement of helium isotopes. This ratio is set in the Big Bang, yet on Earth, we're constantly making helium-4 from radioactive decay. And so this value is very low on Earth, except at certain hotspots around the world. And in fact, Iceland was such a hotspot, Hawaii is such a hotspot. And I got very excited and I said, well, if you've measured the helium, have you ever measured the D to H in these rocks that preserve the interior material? And he said, no, that would be very difficult to do. You'd need one of these brand new ion microprobes that have just come out to do it. And I said, Hawaii just got one. And so I got very excited and started to actually do some geology. And that's where the kid in the candy shop, the kindergartner, I'm learning new techniques, go out in the field. And I went with the volcanologist and I looked at dismay at all of this and said, I'm sorry, all these rocks look exactly the same to me. How do I know which ones? And he said, he smugly crosses his arms and said, that's why you have me along. And I said, you're not a very good teacher. Eventually, he did show me what to look for, some of the green olivine crystals. I decided I'm probably not a geologist. I was not going to climb this hill under any circumstances, but it was fun to participate and take notes. And I participated through the whole process. You take the rocks, you grind them down, you pick out the little olivine crystals, and that's tedious under a microscope. Green one, black one, white one, and then when I bumped the paper and everything went flying, you start again. But here's the UH ion microprobe. You have the ability to measure composition and isotopic ratios at micron scales. And so a postdoc of ours did this, and what she found from some samples from Baffin Island and Iceland was that the Earth's interior is lower than the Earth's oceans. And this is still only an upper limit. How much lower, we don't know. So what we're seeing is isotopic fingerprints are really good tracers of what is going on, but each isotope will trace a different physical process. So we've seen the story of D to H, but there's other isotopes that we can look at. And this is where we bring in some work from the meteorite community, the cosmochemistry community. They had a problem. They were trying to understand why the different isotope fractionation for oxygen. Now, oxygen has 3 isotopes, oxygen 16, 17, and 18. 16 is the most abundant. And the theory they came up with to explain the trends they saw in oxygen was that most of the gas in the solar nebula was CO, and the ultraviolet light from the young star can photodissociate the CO, and we get C and oxygen. The oxygen will combine with hydrogen in the disk and eventually form water. Now, the wavelength at which the different isotopologues of CO break apart, so C16O, C17O, C18O, is ever so slightly different. So the most abundant one, C16O, uses up all of the ultraviolet light pretty quickly. And as you get deeper and deeper into the nebula, the only light that's able to break apart things is going to be creating water that is heavier with oxygen 17 and 18. So that is going to depend on different physical processes than the D to H physical processes. Nitrogen can do the same thing. It could be the same self-shielding like oxygen. It could be different low temperature processes. But the point is, these are all different tracers of what's going on in the nebula. And then finally, noble gases get trapped in water when water freezes at low temperatures. And how much of each species will depend again on the temperature. So if we really want to understand what's going on, we need to make measurements of several species. But that's just the chemistry side of things. Remember, we still have the problem on the physical side, the assembly of the solar system. How do we make some sense over which models are correct there? Well, that's where an interesting discovery in Hawaii came about in 2013. Richard Wainscoat has been using the Pan-STAR survey to hunt for potentially hazardous asteroids, but it's finding lots of moving objects. And he came into my office one day and said, we've got a new long period comet coming from the Oort cloud that's very unusual, he thought. He said it's near perihelion, it's inside the orbit of Mars, it hardly has any tail at all. Is this unusual? And I got really excited because comets that come in from the first time from the Oort cloud typically have really long tails, they're rich in CO. And I said, yeah, this is pretty exciting. And we ended up naming it a Manx comet instead of saying long period comets coming in near perihelion with barely any tail, which is a mouthful. We use Manx as short for the nearly tailless cat. So this very first one that we looked at was a real surprise chemically. Most comets, and all comets in fact, when you look at the reflectivity of light from the surface, from the in the visible wavelength region, it just gets redder and redder and redder as you move out into longer wavelengths. This one did not. It had an absorption near 1 micron, which the colored points here are actually the Manx, which are very typical of rocky inner solar system asteroids shown in the gray. And this type of material cannot form in the presence of water, yet this thing had a tail and it was behaving as if ices were sublimating and creating the tail. So our thought is that this may have been something that formed in the inner solar system near the water ice line. The giant planets interacted with it, ejected it outwards towards the Oort cloud, where it has spent most of the age of the solar system. And then just like any other Oort cloud comet, eventually a nearby passing star interacts with it gravitationally. And here we have a nearby star interacting, sending it back into the inner solar system for us to discover. Now, what was especially exciting about this is this gives us the possibility of testing some of these dynamical solar system assembly models. And this is just a graphic that is showing a few different models. This one is showing 2 different models, the Grand TAC model, which starts to assemble the giant planets early on. And so here we have a gas and dust disk at time 0, and this is just showing icy planetesimals. The water ice line would be here. Anything inside is rocky. As the gas giants grew in the disk, if they moved around inwards, they could gravitationally interact with the tiny planetesimals, throwing icy things outwards and inwards. And likewise, the rocky material can get tossed outwards. Eventually, the giant planets in this model stopped and then moved back outwards, and then the gas disk went away. A different model called the Meech model, which was actually developed first, then looked at the effect of these giant planets, which started at these distances from the star, looked at the effect of interacting on the leftovers that were outside the giant planets, and that causes perturbations with the giant planets, a little bit more scattering of planetesimals till we're left with today's solar system. Other models, such as those proposed by Sean Raymond and Isidoro, show that generically you can build the giant planets and have them scatter planetesimals without the giant planets moving. So that the net effect is you will always scatter planetesimals. Where you will scatter them from, however, may depend on whether things move or not. So the idea is that maybe we can use these Manxes as a test of dynamical models. So Pan-STARRS is discovering a lot of Manxes. It's got this huge array surveying the sky every night. Once we discover Manxes, we follow them up, we get their brightness with the Canada-France-Hawaii telescope, and then look at them with an 8-meter to try and get their colors, their spectral reflectivities. And this is the work that my thesis student is doing. And so here's a summary of some of her results. This gray region here is where all comets fall. They're just red, but not dramatically red. Here, underlying is a typical rocky inner solar system asteroid. Here's that one Manx that we saw first off. We've got 2 now that show this rocky spectral feature. But what we're seeing is the Manx have a huge range of colors, meaning there's a lot of stuff coming in that doesn't look very cometary that has sampled a large region of the solar system. Another interesting clue that helps us unravel the story is, again, from the meteoriticis, another cosmochemical clue. And this was a study to look at some carbonaceous and non-carbonaceous meteorites. So they formed, and if you look at the isotopes, these are just, it happens to be molybdenum and tungsten. But what you can see from the two different groups, carbonaceous are in blue in both cases, and the non-carbonaceous are in red. What you see is they're distinctly different chemically. Yet when they were age dated, they formed at exactly the same time. They had the same ages, and they coexisted between 1 to 3 or 4 million years from the start of the solar system, and they did not mix, and they were kept chemically distinct. And so the interesting thing about this study was the proposal of how this was done. So it was proposed in this nice diagram that's summarized by Steve Desch. It was proposed that Jupiter formed very early, around 3 astronomical units from the sun, and it opened a gap. And then material that would normally be flowing inwards can no longer flow inwards because now you've got a pressure bump here. So we have reservoirs that form outside the gap and inside the gap. This dark blue region represents the ice line, which will move inward over time as more and more material falls down onto the disk and it gets cooler in the interior. Maybe the Manxes formed near the water ice line boundary. So putting it all together, Jupiter opens early, impedes the flow of icy material. Earth and terrestrial planets, our habitable planet, forms in the warm inner disk where there's no ice, it's just gas, so it's hard for Earth to capture gas. Jupiter is going to throw stuff around regardless. Where it throws it around from will depend where it formed and if it moved. So Jupiter will certainly throw things into the inner solar system. It would have hit Earth, and also will get captured in the asteroid belt. So Earth either formed and captured volatiles from just the gas, or it could have been delivered by this rocky and icy material that got scattered by Jupiter. Which is it? What are we going to look at to solve the problem? Well, in fact, what you need is some sort of icy body that records the history of the solar system. We know where it formed, where it ended up. We need it close enough to observe in detail. We want it small enough so that it hasn't been heated and it hasn't changed. And as you saw, we need to make a lot of chemical measurements, a lot of isotopic measurements, and that is hard to do from the surface of the Earth. So really, the ideal place is to look for things that are wet in the asteroid belt. Look at the water in the outer asteroid belt. Do we have evidence of water out there? Well, certainly we've seen from various missions and ground-based studies that absolutely, yes. You know, the various missions that have looked at Ceres and Vesta have shown that there's water, a lot of evidence of water, both chemically, looking at some of the geological structures on the surface. Some of these regions, pitted regions, look like there was once water, maybe sublimating. Some smaller asteroids that are still pretty big, they've been heated, have shown water frost on the surface from spectra. So there's certainly evidence for water in the belt. One has to be a little bit careful about whether or not you call it water evidence. Here's something that was discovered by Pan-STARRS. The asteroid itself was not discovered by Pan-STARRS, but it was found to have this beautiful tail in 2019. This is the HST image. But when you looked at the tail, and the tail has formed several times, but when you look at it, and this graph on the bottom shows the brightness of this asteroid. The dark line is if it was just a naked asteroid with no dust. The colored data shows the brightness when at all times, and if it's above the dark line, that means there's dust. Along the bottom, the scale represents position along the orbit. 0 means it's closest to the sun, 180 aphelion, farthest from the sun. The time it has the tail is not always coincident with temperature. It happens any old time. So this one is not believed to be due to water or cometary activity. It just may be spinning so fast that it's throwing material off of the surface. So one has to be a little bit careful on deciding what is water and what is not. However, there is a class of objects in the asteroid belt that is water rich, and these are called the main belt comets. They develop tails just like regular comets, although the tails are weak, and they develop it multiple times every time they pass perihelion. They're considered small, so they haven't been heated. And there's about a couple of dozen of these now, 13 of which that have had multiple passages. So we know that there's ice in these guys. So these are the ones that you really would like to visit with a spacecraft to understand the origin of water. So the idea would be to fly a mission to one of these main belt comets, do the experiment, look at the different isotopes, compare it to different dynamical models and chemical models. And just if you recall that figure that we saw from the Rosetta mission, it might agree with several dynamical models and several chemical models. So we can't distinguish which one is correct. But once you add another isotope, you'll get similar results, agreement for some of the dynamics, some of the chemistry, and some of the agreement will be the same as other isotopes. And we can keep going down until maybe you get a possible solution, or maybe not, which means we don't have the right models. So a bunch of us have been trying to propose a mission to go to the asteroid belt called Proteus. And the name was chosen because Proteus was an ancient god of the seas, but it's also a name for one of these beautiful changing flowers in Hawaii that almost look fake. They look kind of like plastic because it has so many forms. And the idea of this mission is to take a solar-powered spacecraft and launch a rendezvous with two main belt objects, one of which is a binary asteroid, binary MBC, and the other one is not, fly past a couple of other members of their families and do detailed isotopic measurements by staying with these for on the order of 7 to 9 months. And at the same time, doing some of the standard characterization of these bodies with exquisite imaging abilities. So hopefully this mission will get funded so that we can explore the water in our solar system to try and understand where Earth's water came from. However, I want to mention some other possibilities, areas of science that we have missed in the mission realm. So far, we have talked about tracing what happened in the protoplanetary disk by looking at things that probably formed in the Kuiper belt and got brought into the inner solar system. We've had missions to Jupiter family comets, one to a Halley type comet that probably formed at a different region. What we're missing so far is we've never visited something that's coming in for the first time from the Oort cloud. We have never visited a Manx because they're faint, hard to see, recently discovered. We hope to go to a main belt comet. And then what about the interstellar objects? These are the same leftovers from processes of building a solar system elsewhere. So we can do some really interesting science if we can go to some of these different types of objects on the long period comet orbits. The problem with this is there are a lot of challenges to doing this. First of all, let's take a look at this graph. This just shows discovery of long period comets as a function of time. These are discovery year, and this is the distance at which it was discovered. And you can see in the 1950s up through the 1980s, you mostly did not discover these things much farther than 5 AU. And you say, well, yeah, that's quite far out, but it isn't really, because things on this type of orbit, they take a long time coming from the outer solar system, and they go really fast through the inner solar system. So this is not much time. Here you can see in the mid-1990s, a lot of surveys came online and we suddenly started to discover a lot of new things. The Pan-STARRS discoveries alone are the red ones. The Manxes are now shown in blue. We're now getting to the point where we're discovering them maybe 15 to 20 AU, and sometimes you can dig back in the surveys and discover an image where it was seen but not discovered much farther out. So we might now get them 10 years before perihelion. These things are not in the plane of the solar system. They can come in from any direction. That makes it challenging for a mission. Also, many of these things coming from the outer solar system are very active. And as we saw with the EPOXI target, you can see these jets coming out on the night side. All of these specks are not, in fact, stars. Those are big chunks of material, tens of centimeters in size. Plus, if we really want to understand these for a mission, you want to characterize them, they're really small. So this is going to be science that you have to do in situ with the spacecraft. So let's take a look at some of the challenges. First of all, if you fly past something at very high speed and you have all this debris around the nucleus, it's very dangerous. Giotto was destabilized by a 1 gram grain because it flew past it at nearly 70 kilometers a second. We're going to have to change how we plan missions. Right now, if you put in a proposal for a mission, from the time you propose to the time you might launch is typically 6 years or longer. You really need to have a new type of mission where the spacecraft is ready to go, either on Earth ready to launch or floating in space all ready to fly. Here's some of the problems. Ideally, for one of these rare objects, you want to have a rendezvous, meaning you stay there, you orbit, you take time to collect data. So what else on this chart is the launch energy, how much energy to launch, and that's equivalent to cost. This is the encounter speed. Ideally, you want 0. And the color scale shows the percentage of objects that you could launch within half a year of perihelion and have a reasonable flight time of less than 10 years. If you notice, dark blue is 0. There is no probability you're going to get a rendezvous, just none. If you are willing to pay the price of a high launch energy and a high encounter velocity, meaning you go past really fast, you can get 90% of the newly discovered objects, but you really don't want the high encounter velocity if you can help it. If you want to have a low launch energy, but will accept high encounter velocity, only 20% are accessible. If you're willing to pay the price and you want a kind of low encounter velocity, you'll have a small percentage, but you may have a long travel time, unless you get really lucky. And this is this comet C2017K2 that pre-discovery observations were 10 years from perihelion. It just so happens there's a trajectory that has it past Jupiter, which gives it a boost. And so you could have a low flyby speed, but a long travel time. So let's take a quick look as I finish up what the challenges are for interstellar objects. They are moving even faster. If you recall, Oumuamua was discovered on October 19th, 2017. It had come from above the plane of the solar system, and this is just a blow up of this inner region. It had passed inside the orbit of Mercury, had passed the Earth on the 14th, and it was discovered on the 19th outbound. And it passed very close to the Earth, about 63 Earth-Moon distances. Looking at the timetable, it was discovered the 19th. It wasn't realized it was interstellar and that important until the 22nd, at which point everybody scrambled. They're writing proposals, getting them approved on 8-meter style telescopes and other big telescopes. And most people weren't starting to observe until about the 25th. And then most of the observations stopped by the 28th. Because if you look at the brightness as a function of time, the discovery, we're writing proposals, you're starting to observe. By the time these observations ended, about a week later, it has dropped in brightness by a huge amount, and only the space observatories continued to follow it for a couple months, but by then it's extremely faint. So this is a terrible case. You only have a week. That is not enough warning to do much of anything. The second interstellar visitor was a lot better. It was discovered prior to perihelion by about 3 months. It did not get as close to the sun, so it wasn't moving as fast, and it has been observed for about 1.5 years. And in fact, we just got some more data last week on it, but it's extremely faint. It's fainter than 28th magnitude at this point. So what have we learned from these interstellar objects? Well, the first one was rather unique. I mean, it looked like a comet. It was quite small. If you assume it's the same reflectivity as a comet, it was red, just like a comet is. What was very unusual was its highly elongated shape. No dust or gas was observed, but it was inferred that there must be gas because it was accelerating as it left the solar system at a level that was typical of comet outgassing. We don't know if the shape was just elongated or if it was more of a flattened disk. 2I, on the other hand, looks like a small typical comet, although it is depleted in some of these carbon compounds, but we see that all the time in comets. Very CO rich. It actually has split. It's split on 2 occasions, so there's a couple of different pieces, and it's had an outburst. But other than that, if you didn't know its orbit, it just looks like a regular comet. There's been many interpretations, especially for Oumuamua, in part because of the strange shape. Interpretations on its formation, either this is just a piece that was ejected from another solar system that has a strange shape because it was tidally disrupted by giant planets, and then the surface ice is vaporized, to more exotic things such as a star in its dying phases sort of melts the surface and it gets a strange shape. To more recent hypotheses, maybe it's a strange molecular hydrogen iceberg or a fragment of a nitrogen-rich Pluto from another solar system, to even more exotic, unsubstantiated alien visitors. So the idea is, if we want to do some really compelling science with these, we're going to have a completely different type of mission, one that's ready to go. And maybe, since we can't do a rendezvous, you need to have a multi-spacecraft architecture where you have a lot of small spacecraft that you're willing to fly close, even though it's risky, where you can actually see, do multiple experiments at once. And this was just from a Keck Institute study showing what you might be able to do with either an interstellar object, Manx, or a long period comet. You have a mother spacecraft with a whole bunch of smaller components that get released at various times to do different types of science, and all of the data is relayed back to the mothership. So I think we have, with all of these exciting small bodies, we have the potential to understand the process of building solar systems, perhaps habitable worlds, and maybe even understand where water comes from in our solar system. But as you can see, it's a very interdisciplinary field, from geology, geochemistry, cosmochemistry, looking at the chemistry in disks and dynamics. So I think the excitement is here, and we're on the verge of getting some insight into how habitable worlds form. Thank you very much.
Okay, so thank you again, Karen, for a beautiful, wonderful talk, very inspirational. I have 100,000 questions, but maybe
I don't know if we have enough time.
Maybe the first one. So what can we learn from the moons of the gaseous planets, the outer solar system planets, and the Plutoids, the KBOs, as a function of mass, right? So there should be a variation in the mixes of the isotopes, right? As you look for very, let's say, movable objects to very solid objects. And there is, of course, this inference problem, like what feeds what in the end, and what gets moved around to be able to feed what system and planetoid. So can you talk a little bit about this?
Well, part of the problem is, if you're talking some of the icy moons, they're often too big. They've undergone some thermal processing. I mean, even Enceladus, it's really small, but it's had some tidal processing. So, it's chemically different from when it started. So you want to have something pristine and tiny that has not been thermally heated. And of course, some of the outer moons could be captured from somewhere. But anytime you're doing isotopic work, But, comets, you can do some isotopes from the ground, but the level at which we're trying to get measurements here really requires an in situ spacecraft. And of course, the Cassini mission did have a spectrometer that looked at Enceladus, so they do have isotopic measurements there. So these are all missions. Some of this science is going to require a lot of missions, and it's hard enough to get a mission to a comet. Now you want us to go to all the small icy moons with isotopes. I'd love it. But part of the problem is you wouldn't know, you kind of need to know where they likely came from. Well, no, actually, I just think having missions to all of the moons would be great. Let's leave it at that.
I agree.
You didn't constrain my budget, so I'll just leave it at that.
Thank you.
Dan, do you want to go?
I had a different question about moons. Carlos Rodriguez-Strel, a participant, was asking about, could there be life on any of these moons? And I'm also curious, where should we look? Are you interested in Enceladus, in Europa, in Titan? Is the life going to be identical to Earth? Could maybe say a few words about panspermia, or do you think it might have amino acids that are different? Could there be life based on methane? What do you think?
That is a huge question. Let me break it into pieces. I think the most likely place would be Europa, because all the models suggest that you certainly probably have at least 10 kilometers of ice over the ocean, but you have an ocean. The models suggest that you likely have a rocky bottom to that ocean, and you probably have hydrothermal activity. And it's not resolved where life originated on Earth, although there's a possibility at hydrothermal vents because you have such rich chemical gradients with the seawater flowing beneath the surface and mixing with the minerals and coming out heated. So that would possibly be a good place. What you do not want is a world such as Ganymede or some of the others where the ocean's so deep or the pressures are so high, you don't have that water rock interface. Now, whether or not we could ever get through the ice layer on Europa to get down into the ocean to see the life. I know James Cameron made a short movie clip. I think it was for some mission proposals of a thermonuclear heated probe that would melt through the ice into the Europa oceans and explore them. And of course, he had some fantastic organisms that he drew into the movie. So that's one part of it. I'm not so keen on Enceladus. It doesn't have a global ocean. It's likely a partial ocean. I don't know if that one supposedly has a water rock interface or not. Titan is intriguing. There's probably water ocean at some depth in there, but it's intriguing for the prebiotic chemistry. Now, I believe one of your other questions in there was, could we have a completely different life that's based on some other solvent and some other compounds? And if you actually look at a lot of the compounds, ideally you would like a liquid to remain liquid for a wide range in temperatures. And of course, water remains liquid for about 100 degrees. If you have a compound that's liquid over a very narrow range in temperatures, that means you'd have to have such precise conditions for habitability, it's unlikely. There's only one other compound, I don't remember if it's ammonia or ethane, that remains liquid for nearly 100 degrees. But the problem is it's liquid at such low temperatures that the chemical reactions, the chemistry for life will be very slow. Plus at low temperatures, you don't tend to dissolve organic compounds very well in that medium, although some have proposed that silane compounds, silicon-based compounds, can dissolve in these organics at low temperatures. And of course, people say, aha, Star Trek got it right. We had the silicon-based Horta, yes, but silicon doesn't make nearly the complexity of molecules that you get with carbon. So almost certainly life will look different than we see it on Earth, because every new organism that's ever discovered on Earth that turns out to be the most abundant microorganism ever looks bizarre and different. But I'm guessing it'll probably be more or less the same chemistry, but I don't know. I'm not a biologist. I'm having fun learning about biology though.
Meredith?
Yeah, thanks for a really wonderful talk, Karen. I really enjoyed it. I learned a lot. I wanted to ask you about making the connection from our solar system to exoplanetary systems, because we know that there are disks of comets surrounding other stars that have planets in them. But I've always been struck by differences here, right? On one hand, we don't really know whether there are Neptune planets in other solar systems. We haven't been able to detect them. These disks of comets have very different masses. There's a huge amount of mass in these disks compared to what's in our solar system. And we're dealing with this totally different observational situation, right? Here we can do these really detailed measurements, and in these debris disks of comets, we can only look at bulk composition. So I guess I was curious what your thoughts are on whether we can make any connections and now, and then maybe what observations would be necessary in the future to do better.
Well, yeah, let me start by saying I sometimes motivate this by saying, if our solar system architecture with the gas giants outwards and the terrestrial planets inwards and our asteroid belt and our Kuiper belt and Oort cloud are unique architecture, does that somehow imply that that's a necessity for life? Are we really truly unique? And I think history has shown philosophically that's really dangerous to say that we are unique just because we're here. So I don't want to argue that we need that, but it certainly is one solution to the problem. In terms of observations, I think the short term, I'm really excited about the proposals for the next generation of sub-millimeter arrays, where we can start to get the chemical information and watch planet formation on the scales within the habitable zones of these solar systems, because then we can look at the chemistry and see how it compares to the disk chemical models for our solar system. I think that's going to be the first clue, especially if we can get some isotopic information. So to me, that's the most exciting. But the second most exciting thing would be if we could send a mission to one of these interstellar objects and just get up close and personal, because a lot of the science you want to do really does need to be in situ. Although I have to admit, for even just Oumuamua, if all we had was a spacecraft that could have taken a close-up picture, it would have been really intriguing. And in fact, there were several people that proposed missions, and I know JPL actually looked into it, and it would have been feasible to just take money and build a mission. Even though Oumuamua didn't have much time close to us, you could have reached it by chasing after it at high speed. The only problem is it would have been about 100 AU from the sun at the time the spacecraft got there. And usually the final phases of a mission, you're doing optical navigation to pinpoint your trajectory. And it would have been a faint black thing, very hard to catch up to. And this would have been a many billion-dollar mission. But we have the technology to do this, but I think we need a new architecture for missions where, like the mission in Europe, the Comet Interceptor mission is ready to go and waiting for something exciting.
Yeah, that's really, you answered exactly how I was sort of hoping you would answer, because it seems like these interstellar objects are like one of the few opportunities we're ever going to have to actually take in situ measurements of stuff in other solar systems. So
yeah, LSST is likely to discover about a few a year. And if we discover these far enough out, we should have enough warning to mount a mission to one of these.
Okay, Daniela.
Sorry. Thank you, Carrie. It was great to hear a very broad view of the problem of comets in a very short talk. It was great. What I would like to ask is about the Trojans. I have heard there is a mission to Trojans, I think. And will they have the water that we are interested or not? What do you think?
The problem is, well, first of all, they won't have the instrumentation to make the sort of measurements that we need, You can't do the isotopic measurements. And again, what you need to measure is a known class of objects that would have hit Earth. And the Trojans, we don't know. Whereas things that got captured into the asteroid belt clearly got tossed inwards beyond whatever gap that Jupiter opened up. And those same things would have been tossed towards Earth. So, you know, you might get some measurements if you had a mission that went to the Trojans that could do the isotopic work that would be very interesting from the disk, but you wouldn't have that component that links it to Earth.
Okay, thank you. Thank you very much.
Jorge, do you want to go?
Yep. Thanks for a very interesting talk. So I found very interesting that the isotopic composition of water in Earth is different comparing the oceans to the inside of the Earth. So I was wondering whether that is giving us interesting information on how difficult is the mixing of water between the different parts of the Earth, and at the same time, if it gives us any information on the timing of the water delivery.
I don't think so. All we can really tell is that this material, and for whatever reason that I don't fully understand, and I'm not sure the geologists do, it's the Icelandic hotspot, the Icelandic plume, that is showing the most primitive, unaltered materials. Most of the other hotspots are not as pristine in the helium ratios. So for whatever reason, that's a particularly good source. But you know, some of the ideas suggest that, you know, shortly after the Earth was formed, it had a magma ocean, and then that ocean solidified a bit, you're still going to have liquid magma underneath, and that's an unstable situation. And so they postulate there would have been a magma ocean overturn where this material and the late arriving material would have sunk down to the core mantle boundary, and that may be the material that's being preserved. But beyond that, I don't think there's any way to know about the timing or mixing in the interior. We've just gotten some samples. I'm actually hoping to mount an expedition to Greenland because that's along the Icelandic plume, and some of the best helium isotopic work has been done from Greenland. You know, I'm not someone that's good at scrambling out in the field, but if I get the money to go to Greenland, I'm going to go, even if I'm the camp cook and I take care of the geologists that are sampling things. And believe me, I've had lots of volunteers to say, I'll go with you. So I think there needs to be a lot more work on the Earth side of things. And it's been a lot of fun.
Okay, there are some questions. Let's see, from the Q&A. There is one from Ariel Pastier. He's asking, why did the Earth retain water while Mars did not? Can you ask it?
Well, the Earth's a lot bigger, and you know, a lot of the water from Mars, well, a lot of the water on Mars is still there. You know, it's frozen now. It had huge atmospheric losses on Mars, and so the atmosphere got stripped off. Even with the moon forming impact on Earth, the simulations show that the moon certainly lost a lot of water during that, but the Earth gravitationally could hold on to it, although the ocean certainly would have been vaporized. There was actually some very interesting work done by Steve Moises, who's a geologist, who said that, you know, we may have had multiple epochs of the origin of life on Earth. Even very, very large impacts might not completely wipe it out, because as we go deeper and deeper into the Earth, you know, anytime they open up a new mine shaft, there's usually a new type of microbe that's never been discovered before, and it turns out to be super abundant. So we're just saying that life fills in everywhere. So you could have had multiple periods where the Earth became completely inhospitable, yet life survived. So, you know, very interesting ideas.
Okay, there is another one. It's kind of related, but is the origin of water, this is a question from Abel Mendez. Is the origin of water on Mars the same as on the Earth? I mean, are these the similar, have the similar d over h radius?
Almost certainly, I think the origin of water, however it got there, will be the same for the two planets. You know, the details will certainly be different. The D to H in Martian meteorites has been measured, and it's very high. But of course, that would be expected because there's been huge loss of atmospheric loss on Mars, and you lose the lighter materials first. So if you get water into the atmosphere, it gets photodissociated. The hydrogen will preferentially go away faster than the deuterium. So the D to H in Mars meteorites is elevated. And we don't know about ices on Mars. You need a mission for that. So the answer to everything is you need a mission. You need to go there.
May I jump in at this point just quickly with a question that fits perfectly? What about the Perseverance set of experiments? Do they have the capacity to actually measure some of those ratios?
I do not know. You need pretty high mass resolution, I mean, very high mass resolution to do the isotopic work and very high sensitivity. I don't know. That's an excellent question.
Sean, do you want to go with your question?
Hey, Karen. So great talk. I really enjoyed it. I have a question about asteroids. So you mentioned how none of the asteroids that we know of now represent the building blocks of Earth, kind of the stuff that Earth was really formed out of. But there's reasons to think that Earth probably didn't form perfectly efficiently. And so there could easily be some remnants of it floating around in the asteroid belt or somewhere else. So if you were to design an experiment to try to find this stuff, how would you do it?
Oh, I would get some asteroid experts on board. I think you'd need a multiple rendezvous mission where you're doing detailed in situ measurements, because I think, again, the key is going to be in the isotopes. That would be a really expensive mission. I think I'd rather go after an interstellar object or do the main belt comets to get at the volatiles first, because there you have a target to go to. Whereas your asteroid suggestion means we need to hunt for things that look isotopically and chemically the same as Earth. And I think you're going to have to hunt for them by going to them. So that's going to be tough.
Cool. Ellie?
Hi, Karen. Thanks for the nice talk. I was wondering about plate tectonics here on Earth, if they somehow can be related with the origin of life, and if this is so, then we have to search for other planets with plate tectonics in order to search for life.
Well, on Earth, if you look at Bill Schaap's work, there was certainly life at 3.5 billion years. You see the microfossils in the chert in Australia. There's isotopic evidence of life as early as 3.8 billion years. And plate tectonics did not start that early, because you take a while to build up the whole cycle of the continental processing. The earliest land masses were probably like hotspot volcanoes. So it took a while to get plate tectonics going. On the other hand, a lot of people feel that you won't have a habitable world that could sustain life unless you have plate tectonics going. But I don't think it impacts the origin of life.
Thank you.
Miarka?
Hi, Karen. Thank you for your lovely talk. I was really enjoying, as a biologist, your slides in taking samples in Iceland. It's amazing also to see how this multidisciplinary work can bring new ideas how to understand something so vital as the origin of water. So I was wondering if now that we know that there is these two interstellar objects that has been observed, that probably there is a population of these objects that also has come and passed through the Earth history. And as you know, meteorites are random samples of different kind of objects in the solar system. So I was thinking if in the mind of people that is studying meteorites in the collections, if they think that in certain moment, I don't know, if going to these missions to Antarctica to collect meteorites or the hot deserts as Atacama, we could find a piece of material that could be related with this ISO.
Well, that's certainly an excellent question. And I know I had talked to the cosmochemists in our group before. I said, is there any chance? And he said, in all the meteorites they've seen, there's nothing that's that isotopically weird. They have had a couple meteorites that were initially kind of weird from the perspective that they saw water in them. And so he was totally excited by the discovery of Manx objects, because he said, well, maybe this explains those meteorites. But his opinion was that no, we've not seen any interstellar signature that couldn't be explained by our normal isotopes in the solar system. And the interesting thing about the interdisciplinary perspective, it actually started also from that first field sampling trip I did in Iceland, because my colleague dragged me to a volcanology conference. And I said, am I going to get anything out of this? It's not my field. He goes, this will be great. It's honoring the life career of someone famous. So it'll be at a very good level. And during one of the talks, and it was, they showed a picture of a pyroclastic eruption, a pyroclastic flow, and a light bulb again went off because it was in the thick of the deep impact time. And I said, could I show a slide? Because we have this feature on the comet that we can't explain. And it looks to me exactly like your flow field after a pyroclastic flow. And I showed it and they said, yeah. I said, but do your models work if instead of one atmosphere, we have vacuum, and instead of magma and hot gas, we have CO2 volcanism? And so they ended up writing a paper on volcanic effects on a comet that's only a few kilometers across. So this is what's really neat about the interdisciplinary science. It's like the same as the kindergartners who aren't afraid to ask the weird off-the-wall questions that are seemingly unrelated. And it gives you insight that you would have never had in your own discipline.
Thank you.
Thomas, you have another question? Thomas, you're muted.
Yes, sorry. I was intrigued that you like geology so much now, and I was wondering if you considered going to Australia instead of to Greenland and looking at the zircons and the inclusions in the zircons there, and digging out, I don't know, some, again, isotopic ratio indications for the early delivery of water to, you know, the pre or even shortly post-impact crust, right, which is what, 4.4 billion years old, the oldest, I think.
You know, I talked to Steve Moishes about this because, you know, our earliest evidence of water on Earth is from those 4.4 billion year old zircons. And he disabused me that he said this would not be a good idea. And I don't honestly remember why. Because it seems to me with the technology of ion microprobes getting down to micron scales, that if you can do D to H at that level, why not give it a try? But he said, no, it wouldn't work. And I don't remember why.
Let's ask him. I have another question from the Q&A, which is at the very top now. Terry Bollinger is asking, the high water capacity of Earth's core was surprising. Is this an interaction with the molten iron, or is this due to the interaction with the molten iron?
You know, now we're getting way outside my field, but as I understand it, the Earth's core can't just be iron. There's something else in there. And some people believe that it's, and bear in mind that when geologists inside the Earth are talking about water, it's hydrated minerals, and it may just be H in the core. So I don't know exactly, but I've seen some papers that even hypothesize 100 oceans worth of hydrogen in the core. So in other words, we have no earthly idea how much water is on Earth.
That's a massive reservoir. Yeah, that's a lot of parameter space for the modelers.
Yeah, this is one field where the more you dig, the harder the answer seems, the answer seems to be moving further away. But yeah, I don't care if it's comets that brought ocean water. It's just a lot of fun exploring all these different fields to see if we can make some progress.
Nicely ties in to this one view graph that you had in one of your slides, where you have these model predictions, and then you measure one isotope ratio, and then you narrow down the options, and then the other one leads to fewer and fewer options. And so I want to tie this to a question. So this is now the last question from Dietrich Bade, who is asking, are there any chemical isotopic dynamic indications of matter injected into the solar system from birthplaces of other planetary systems, but both or all or environments like stars we know form in a clustered fashion? Could you actually distinguish, somehow pinpoint, put your finger on some specific indicator or diagnostic that would say, well, this was contaminated by a star cluster environment, or this was not contaminated by a star cluster environment?
This, I don't really know, but I vaguely remember some discussions where some of the cosmochemists, in trying to understand what they see in the meteorites, are talking about galactic chemical evolution and pollution from elsewhere, but I don't know the details well enough to express it.
Okay. All right, Paula. Should we wrap
Sorry,
up?
yes. I think, well, that is the last one.
Julio has
Let me
one.
see. It's about, Julio has one. Okay,
has one,
Julio,
yes.
Julio, go.
Unmute yourself.
Okay. Well, first of all, it was a very interesting talk and a very interesting discussion now. My question has to do, I'm going outside from the solar system to astrobiology, to exoplanets, and to the concept of habitable zone. That if we talk about habitable zone in terms of equilibrium temperature, but I wonder if it is not important to consider also if the planet, exoplanet, has a magnetic field, because we think that magnetic fields are a very important ingredient for the development and sustaining life in a planet. Then my question is that, should we consider also magnetic fields, and how can be magnetic fields detected in exoplanets?
Yeah, I didn't hear all of your comment, but I gather that you're saying, isn't it important to consider magnetic fields when you're talking about a habitable zone? Certainly magnetic fields are important for shielding us from the high energy radiation from the sun, from cosmic rays. But when we have the geomagnetic reversals on Earth, where the field dies down to zero and restarts, it stays down for a long period of time. And we don't see any correlation with mass extinctions when we don't have an active magnetic field. So in fact, most of the radiation protection is actually from our atmosphere. And you need about the equivalent density of material of about 1.25 meters of lead protection for full radiation protection from galactic cosmic rays, solar flares. And coincidentally, the atmosphere gives us just about that amount of protection. So also we've got, for origin of life, you've got the oceans, and you need about 10 meters of ocean water for the equivalent protection. So while the magnetic field has a lot of benefit in terms of preventing the atmospheric loss that we saw on Mars, I don't think it has so much of an impact on origin of life if life originates in the ocean, and it doesn't have an impact apparently on mass extinctions. In fact, some people say it may help spur new evolution, because you'll get, the effect is you may get a bit more genetic mutation during the downtimes on the magnetic field on Earth.
Okay, so let's wrap up here. Thank you so much, Karen, for a beautiful talk, wonderful overview, and very exciting prospect into the future. Thank you, panelists, for joining us today, and thank you for asking great questions. Thanks to the audience for tuning in. This was a very nice Q&A. I want to ask you to fill out again the survey after this webinar is over, and announce the next golden webinar on April 2nd, which will be given by Meg Urey. And she will be talking about black holes, galaxies, and the evolution of the universe. So what grander things can there be? So everyone, thank you again. Please stay safe, stay healthy until the next golden webinar in astrophysics. Bye, everyone.